Okay guys, what I want to do is I want to look at some very basic chemistry, just because it really helps to actually understand all of chemistry. If I were to write a chemistry paper now, I think I would probably study for about half an hour, and I think I'll pass with great colors. And keep in mind, I didn't study chemistry. Okay, the only reason why is because I understand it now. I didn't understand it at high school, and so I had to spend hours, and I probably did very poorly in chemistry at high school because I didn't understand it, and it's not that difficult. So you really can understand chemistry, and then there's just a few things like how do we use the names and what are the specific definitions. But in terms of understanding, it is really not difficult, and it's if you know the basics, the rest really just follows from the basics. Okay, let's start with that. So first of all, if I talk about chemistry, chemistry is really the study of the interaction between atoms. Okay, so an atom is the smallest particle, that retains properties. So you do get smaller particles than atoms, but an atom has the same properties than the element that it consists of. So for example, if the element can conduct electricity, the atom can conduct electricity. Do you understand? That doesn't necessarily mean the smaller particles can. Okay, now different elements, we know things like like hydrogen. I'm not going to go in what the letters represent. We know things like helium, we know ones like lithium, magnesium. Is it magnesium? What's the next one? We know, well, beryllium, yeah. So here's our periodic table of elements, and what I'm going to try and do is help you to understand this table and how powerfully this table can be used to do almost all of the chemistry. Okay, so that you don't need to study things, you just read it off your table. Okay, let's look at it. So first of all, what you need to understand is what is actually the difference between a hydrogen atom and a helium atom. Okay, well, the only difference between them, or the thing that makes them different, is what they have in their nucleus. So an atom consists of a nucleus, and around the nucleus there is what we call the electron cloud. So we've got our nucleus there, and around it we have an electron cloud. Now in the nucleus we encounter what is called protons. So in here we have protons and neutrons. The difference between hydrogen and helium is the number of protons they have. Hydrogen has one proton. If somehow I could give him another proton, I would make helium. What that means is that this is gold. Where is it? There. Ag. Ag is gold, isn't it? Ag is silver. Gold is Au. Yes. Okay. If I wanted to change lead, Pb, into gold, I'll have to take away 1, 2, 3 protons. So I can literally make gold if I could take away protons. The only problem is I can't. Okay, as far as we know, it's not possible to take away protons. That is what makes the difference between the molecules, is the number of protons that they have. That's the only difference. Okay, but so the protons is what we call the atomic number. So since every element has a unique number of protons, that's what makes hydrogen hydrogen, is because it has one. Helium is helium because he has 2 protons. That's called the atomic number. So the atomic number tells us what? Number of protons. So if we look on our periodic table, hydrogen has 1, helium has 2, lithium has 3, boron has 5, okay, beryllium has 4. So how many protons does carbon have?
8, 6.
6. You see it? Doesn't show so nicely for you guys, but you can see it, huh? Okay, that's 6. How many does calcium have? Ca. Calcium, sorry? 20. So calcium has 20 protons. Okay, so that's protons. Simple to understand. It's called the atomic number. Now, the neutrons are roughly the same as the number of protons. Okay, not always. But the protons plus the neutrons gives me my atomic mass. Atomic mass. The reason for that is, okay, so I've told you we also have electrons. Electrons are here in the electron cloud. We'll talk about the electrons, and for the rest of chemistry we'll talk about electrons. All of chemistry is about the electrons, okay? But atomic mass is the protons plus the neutrons, because even though the nucleus takes up almost no space, it has all of the mass. So you consist of more space than you consist of more than, yes, you have more space than mass. It's very, very weird. I don't get it. But anyway, the nucleus has the least amount of space, but the protons and the neutrons are very, 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 very heavy. They're very, 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 very light. But compared to electrons are negligible. Like, you wouldn't even count their weight. So that, or not their weight, their mass. That's how light they are compared to protons and neutrons. So protons and neutrons is what gives the atom its weight, or its mass, sorry. So that's why if we add them together, their mass is roughly the same. Not exactly, but roughly they have the same mass. So if I add them together, I get what gives me the thing's mass. Okay, so that's the atomic mass. Now, protons are numbers. Like if I say 2 and I have 5 neutrons, so let's say I've got 5 protons and 5 neutrons. Or let's say I have 5 protons. What substance am I talking about?
Boron.
Boron. And it should have 5 neutrons roughly. Okay. What should its atomic weight be? Or its atomic mass be? 10, because it should have 5. So it's roughly double. But you'll see here at the bottom, the atomic mass is here at the bottom. And notice that this one's 11. That is because it's not law that they are equal. They're roughly equal, which means boron has roughly 5 protons and 6 neutrons. Now, not all boron particles will have 6 neutrons. Some will have 5. Okay? And when we have a different number of neutrons, it is called an isotope. So it's the same element because it's got the same, boron is defined by that which has 5 protons, but some 5 protons have 6 neutrons, some have 5 neutrons, okay? Some might even have 7 neutrons, okay? I don't know. So what they do in reality, notice some of the values are, I don't know if it's on this table, but yeah, like chlorine is 35.5. That's weird. How can you have 17 protons and then 18 and a half neutrons? You can't have half a neutron. Does that make sense? You can only have, so what scientists did was they went and looked at all it's difficult, you can't say all the protons. They took samples of chlorine and then they looked at the chlorine atoms and they counted the number of protons. We always get the same number. Every atom we get 17. So for chlorine we get 17 protons. But some of them have 18 neutrons, and some of the chlorine has 19 neutrons. So let's say of all of the ones that we found that 50% of the chlorine that we got was 18 neutrons, and 50% of the chlorine that we got was 19 neutrons. Then what we'll do is we'll say 18 times 50%, so 0.5, plus 19 times 0.5, that will give us 18.5. Do you see? And that's why it's called the approximate relative atomic mass. Relative means it is based on, that's where the fraction comes from. Okay, it's a percentage. So for example, some of them, let's see if there's another one here that has a comma. Okay, approximate, because like on this table that we don't have many commas, but if I show you this table, for example, I don't think you can see nicely. Where's the mass on here? I think that's the mass there at the bottom. I don't think you can still see it. I don't want to increase. Can you see it now? So for example, notice chromium has 51,9961, and it should have 24. So if I look at the difference between 24 and 51, it's about 27. So most ones have about 27. No, actually it's almost 52. So most have about 28, because 24 to 52 is 28, but some have less. That's why it's just a little bit less than 52. You understand what I mean? So maybe just 1% has, instead of 28 neutrons, they have, and so the effect is much smaller. So it's leaning towards whichever one has the most. Okay, so I don't want to say too much, it's not that important. Okay, nevertheless, that is what we'll use if we wanted to know the mass of helium. We can literally just read it off our approximate table. Helium will have a mass of 4. And I could think of it as 2 protons and another 2 neutrons to get into 4. Okay, but again, that's not so important. What does become important now, however, is that we now define some concepts. We define the concept of a neutral element. The thing about neutral elements is they do not exist. Okay, but let me define it. A neutral element has the same number of protons and the same number of electrons. So let me talk a little bit about the electrons. So the electrons are appear in the electron cloud. Now we'll look a little bit more about what the electron cloud looks like, the structure of the electron cloud just now. But a neutral element is an element that has the same number of electrons and the same number of protons. I said they don't exist. I lied, sorry. They do exist. These are the only elements that exist with the same number of protons and electrons. Okay. Oxygen cannot exist if it has the same number of protons and electrons. If it exists as highly unstable. Okay, and I'll show you, you'll understand why in just a minute. Okay, so helium, neon, and argon are the only 3 elements that exist with the same number of protons and electrons. This whole group is called the noble gases, exactly for that purpose. The other elements, because they, well, no, it will make a little bit more sense if I explain. Now, the moment I have more protons, so the number of protons is more than the number of electrons. Okay, so here it was equal, so I used n and n to represent the number. here I've got more protons than I have electrons. We call that thing positive. And the moment I have something if it's not equal, it is called an ion. So this is not an ion. If I have the same number of protons and electrons, I don't have an ion. But the moment I have a different number of protons and electrons, I have ions. If it is positive, it's a positive ion. In other words, I've got more protons than electrons. It's called a cation. If I have more electrons than I have protons, let me do this for the P because it's going to be confusing a bit later. If I've got more electrons than protons, then I am defined as negative, and I'm called an anion. So see here, ion means it's charged, cation means it's positively charged, anion means it's negatively charged. Okay. Now let me explain a little bit about what the electron cloud looks like and how the electrons orbit around it. So if I have, again, my nucleus is very, very, very small, while my electron cloud that appears around it is really very big. So there's my electron cloud around the nucleus. Now your electrons start off as equal. We can assume it's equal, but now be careful, even though equal to the protons. Equal, so the number of protons and the number of electrons will start them off as equal. Okay? But that just means the element has to start with the same number of protons and electrons. It doesn't mean that element can exist as a substance yet. In other words, I can't touch. The only substances I can touch that has the same number of electrons and protons are these three substances. The rest, I can't touch it. I can't work with it yet. So what I do have is that the element itself has the same number of protons, the same number of electrons to start with, but in order for it to be a substance, something I can work with, something needs to happen first. And let me show you what happens. So the structure of the electron cloud is that the electron cloud is divided up into energy levels. Now we'll just work with the first three energy levels. I'll write it from the bottom up. So I'll have energy level 1, energy level 2, and energy level 3. Now what that means is it's the distance that it is away from the center of it. So in other words, I can almost, not 100%, it's not 100% accurate to say it like that, but this could be energy level 1, this could be energy level 2, and this could be energy level 3, just as an example. There's more energy levels, but we only at the high school look at 3 energy levels. Now in energy level 1, okay, we can only have 2 electrons. So energy level 1 can only take 2 electrons. The moment I have more than 2 electrons, so there's 2 in here, they start going into energy level 2. Energy level 2 can only take 8 electrons. Okay? The moment I have more than 8, I start flowing into energy level 3, who can and will also only go up to 8. Okay. Energy level 3 can take more than 8, but will only go up to 8 more. Okay. Now look at our periodic table. Energy level 1, energy level 2, and energy level 3. 1 electron, 2 electrons. Now I go into the next. This one goes into his second energy level. Second energy level, second. This one has a full energy level. So this one has a full energy level 1. This one has a full energy level 2. This one has a full energy level 3. And then we go into energy level 4. I lied. Energy level 3 can only take 8. The moment, so sorry, let me just correct myself. We'll go up to energy level 4, but again, so in energy level 4, we'll only go up to 8 again. Okay, so it can take more than 8. I think it can take something like 24. But again, we'll go energy level 1, energy level 2, energy level 3, energy level 4 takes 1, 2. Now these are the ones that we're not necessarily going to look at. 3, 4, 5, 6, 7. Krypton has a full energy level, but not really, and we don't have to understand that, okay? The way in understanding energy level 1, 2, and 3 as filling up the energy levels is completely sufficient to understand all of the chemistry that we do at high school, okay? So that's the idea. Now, in my first energy level, or when I'm in an energy level, if I have electrons there, electrons come in pairs of 2, okay? And when they are in pairs, they spin. So I get 1 electron. So in here, so let me draw energy level 1 for you here. So I'm blowing it up. So here's energy level 1. Okay, there's 1 electron in energy level 1, and here's another electron in energy level 1. You see it? And if the one spins this way, the other one spins that way. Make sense? Okay, now this pair and the way that they spin is called an orbital. Okay, so these two will stay in this little region of space always, and we get 2 types of orbitals. We get s orbitals. An s orbital, why is this one? Okay, an s orbital has a sphere shape. In other words, these two, they can appear anywhere at any moment. But they jump like in and out of space. Like any moment they can appear in anywhere. There's no way to know where they are, except you can contain them into a ball, and they will always appear somewhere in this ball. Does that make sense? So the space wherein they occur is in this little ball. Okay, but we also get other orbitals that look like this. Okay, these orbitals look like this. Let's see if I can make it a bit smaller and a bit darker. Okay. Okay, so they look like this. Again, it's kind of, if you could see it as 3-dimensional. I don't know if you'll be able to see it, but it's almost like a sphere, but it's almost like if you could take a balloon and you can twist it in the middle, and you imagine that shape you will get. That's what the p orbitals will look like. Don't ask me why it's called p orbital. S orbital makes sense, sphere. Okay, why it's called a p orbital, I don't know. Orbital, but this is what it looks like. Again, you can only get 2 electrons in there, and they can be anywhere in this type of space. Now the nucleus is still here in the center. So if this is my p orbital, okay, my s orbital would be here. Why doesn't it draw my s orbital? Okay, here in the center. You see it coming up there a little bit. Okay, so the s orbital is here in the center, the p orbitals come here. Now the p orbitals, you'll notice now if we go back, the moment I go into an energy level, the first orbital that I will have will be an s orbital. The next orbital I will have will be a p orbital. Then I will have a d orbital and an f orbital, which we don't have to do because they only appear from energy level 4 upwards. So don't be too worried about that. So in other words, if I go back to my energy level 1, the first 2 electrons will go into an s orbital, but they are only 2. So in my first energy level, I'm going to represent my orbitals with a little box. And so my first, okay, I'm doing yellow, my first orbital will take an electron. I'm just going to put an electron as a little tick mark like that. So he can take 1 electron, 2 electrons, and then I'll go into my next one. So this is an s orbital, and I call him 1s because he's in energy level 1. The moment I go into my next energy level, what is going to be the first orbital to fill up? S orbital. So I'm going to have an s orbital to fill up, and then I'm going to have, remember now I've got 8 there, 2 of them is going to go into the s orbital. Now there's still how many left? 6. Now those 6 will go into 3 p orbitals. There will be, so they are in energy level 2, there's 3 p orbitals, and they look like this. So I showed you what they look like in terms of shape, what they look like, but there's 3 of those, and this is how they go. One goes, so do you notice it's got a top and a bottom? Okay, so one goes, has a top and a bottom. Then there's another one that goes left and right. Then there's one that comes, and now imagine I can't draw 3D, but then there's one that's coming out of the page. I'll make him a little bit darker. And one that goes into the page. He's there at the back. Can you imagine if I took 3 sticks, I plant one like this and I make a cross like that. Now I take another stick that points towards me. Do you understand what I'm doing? So now that's the one orbital is the one that goes up and down, another orbital goes left and right making the cross, and then another orbital comes towards me and away from me. So in other words, as if I'm putting my arm out like that. Make sense? Are you all seeing that picture? Okay. So in other words, there's one that goes here at the back, one that comes out here in the front, one that goes there, one that goes there. Each one of them have, so there's not one electron here and one electron there. They can be anywhere at any time in that region of space. Make sense, huh?
Yes.
Cool. So I will fill up 1 in each, and then I'll start filling up a second one in each. The moment I have another electron, I'll fill up a s orbital. So this is called the second s orbital. This is called the second energies levels p orbitals. And this is now the third s orbital. 2 goes into there, and then I'll start filling up p orbitals. 1, 2, 3, 1, 2, 3. Did you see again how I did it? I gave 1 to each orbital and then I started over. But it's not the same with the s. We fill up s, then we go into p. Make sense?
Yes.
Okay, cool. Again, these aren't that important, but it does become helpful in just a minute. Now, all elements want to have their energy levels completely full. So in other words, all energy levels, all elements want absolutely no extra. So they don't, the energy level must either be full, the highest energy level, or it must be empty. Does that make sense? Either full or empty. If it's not full and if it's not empty, I can't exist as a substance. Okay? I must somehow get electrons or give away electrons. And that is what all of chemistry is about. Getting and giving away these electrons. So let me quickly show you if we draw this energy level now for helium. Okay, so here's helium's energy level 1. Okay, Helium, if we go and look at our table, he's got 2. What is this? This represents protons. So he starts off with 2 electrons. So he goes and he fills up his first s orbital with those 2. Does he have his energy level full?
Yes.
Yes, he only has 1 energy level. Okay, now we go and look at something like lithium, which is the next one. He has 3 protons. So again, we look here. He's got 3 protons. So he has how many electrons? 3. Okay, so he fills up his first one, and then he goes to his next one. Now, notice here, lithium now has an option. Is his highest energy level, which is now the second energy level, is it full? No, he's in energy level 2. How do we know? We can look at the row number. He's in second energy level. Okay, second energy level needs 1, 2, 3, 4, 5, 6, 7, 8. He only has 1 in that one. He has an option. He can either get electrons. How many does he need? He needs 7 because he only has 1, or he can give away 1. Which do you think he's more likely to do?
Yeah.
He's more likely to just give away that electron. If he does, how many electrons will he have? 2 electrons. How many protons does he have? Sorry?
2.
You can't give away protons. If you have 2 protons, you're helium. You're not lithium anymore. If he gives away 1 electron, how many electrons does he have? 2. How many protons does he have?
3.
He still has 3. You can't change your protons. Remember, protons is my atomic number. 3. That cannot change. So now notice, what do we notice? We have more protons than electrons. What does that make this? A ion. What type of ion? Cation, because I'm now positive. I have more protons than electrons, so now I am a cation. Oh, not like that. Now I'm a cation. Okay, do you see that? Okay. Now, a cation is a positively charged ion. Okay. Now, I want to show you how powerful the periodic table is. Just so that we understand each other when I'm talking now, valence electrons is the word I used for the number of electrons in the highest energy level. So valence electrons is the number of electrons in my highest energy level. Now, there's something else that's also going to be helpful. It's called the octet rule. Who knows what the prefix oct represents?
8.
8. So there's and what do you think that 8 refers to? The number of electrons in the outer shell. I see you use a different word, the outer shell. The octet rule is the fact that all elements want 8 electrons in the outer rule. Now, obviously it's the exception of everyone in number of these 2 elements. Actually, these 3. Okay, and the reason why is because beryllium has 4 electrons, so he goes 1, 2, 3, 4. There's beryllium. Okay, now he wants 8, but he needs to get 6 in order to have 8. Okay, who's going to give him 6 electrons? Whoever has 6 electrons only needs 2 more. Notice, do you understand what I mean? So beryllium would much rather than, okay, I'll give away 2 and then I'll only have 2 in my outer shell. The next one, what was that? Boron. Boron has 5, so 1, 2, 3, 4, 5. In order to have 8 in his outer shell, okay, so remember when we're only looking at the outer shells, the valence electrons, I need 1, 2, 3, 4, sorry, 1, 2, 3, 4, 5. Okay, I have 3 in my outer shell. I want 8, so I need 5. Who's going to give you 5? Because if they have 5 to give, it means they only need 3 more. So who's more likely to get the 5? Are you going to get his 3, or is he going to get your 5? You understand what I mean? So he's more likely to give away this 3. Now the moment we get to carbon, now it becomes interesting, because now I have 1, 2, 3, 4. I need 1, 2, 3, 4. So carbon is just as likely to get 4 than give away 4. And therefore, rather what starts happening from carbon onwards is they start sharing instead of giving. Okay, and we'll get to that. That's now called, before, if I get electrons, it's going to be called ionic bonds. Because I become an ion, because I have more and I give, so it becomes ionic bonds. And when I share, it's called covalent bonds. In other words, I still get electrons, but I'm sharing it. And so there's a little bit of a difference, but it's really fun, guys. You'll see. So the octet rule is just the idea that I want 8. If I can't get 8, I'll give away what I am. If I can get 8, I get it by adding more electrons. Okay. So what can I now say about it? Okay, so notice just now, the power of the periodic table is it gives you all the information. First of all, the row tells me in what energy level I am. Energy level 1, energy level 2, energy level 3, 4, 5, 6, 7, etc., etc. The column, the Roman numeral up here, tells me how many electrons I have in my valence structure. So here, I have 1 electron. I have 2 electrons. This one has 3 electrons. All of these in their first 2 orbitals has 3. So the s orbital has 1, 2. The p orbital has 3. This one 1, 2. So how many valence electrons does sulfur have? Sulfur is S. Can you read Roman numerals? That's maybe the question. What is that value there? What? What did you say? 5.
Asking about the number of
valence electrons. What is that value, guys? Can you read that? I'm sorry to take the mickey out of you if you can't, but it is a little bit fun.
It's 6.
Why is it 6?
Because that's how you write 6.
Yes.
It's group 6. It's in
Huh?
group 6. It's in group 6.
This is group 6, but why is this a 6?
Isn't it giving away 6?
No, I'm asking
V is 4.
if V is not 4. V is 5.
Oh my goodness. Okay, fine.
So V is 5, so 1 more. So I is a 1, 2 I's is a 2, 3 I's is a 3. Makes sense, huh? Now a V, if the I is in front, we subtract it. So this is 4. V, so it's 5 minus 1. If the I is on the right hand side, I add it. So this is 5. 5 plus 1 is 6. 5 plus 2 is 7. And notice here, V8. So notice, sorry, not V8, V3 gives me a 5 plus 3. Makes sense, huh? Okay, so this is, these all have 8 valence electrons. Can you see why they are completely satisfied? They've got their structure full, they don't need any other element. As a matter of fact, helium, neon and argon are called ideal gases because they don't mix. They don't combine with any other thing. They don't want to. I've got my electrons, I don't need you. Okay, noble, isn't it? Okay, very noble. Okay, so here we have our noble gases. They don't mix. You will never find something like argon oxide. It doesn't exist. Neon sulfide, no, they are just neon. That's just helium. Okay, so the rest of the substances always needs another atom. Always. They cannot exist as an atom by itself. They need something else. Okay, now let me give you an example. So imagine we have lithium. Okay, lithium has 3 protons. He would gladly give away, because if we now look at lithium lithium here. Let's do it like this. There's our structure, like that. So lithium has 1, 2, 3. He would gladly give away this one, isn't it? So lithium has one on offer. Who wants my electron? Who wants my electron? So he's willing to give away his electron. If he gives away his electron, what does he become? What did we call him? A cation. He becomes positive because now he's got more protons than electrons. Now let's look at something that will gladly take his electron. Fluorine. Fluorine, if we do fluorine, fluorine looks like this. Fluorine, if we do his energy levels, so there's energy level 1 is filled up, 2, he gets 1. So let's just count here. We count here 7. If we go back here, 1, 2, 3, 4. No, not 7. Oh, that was the 7 valence electron. Sorry, 9. Sorry, thank you. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. He just wants one more. Just one more, please. I just want, then I'm happy. Okay, so fluorine would gladly take an electron. If fluorine takes an electron, he's got 9 protons. If he takes an electron, how many electrons will he have? 10. He starts with 9, the same. So if he takes one, so what does he have more? He's got more electrons. That makes him an anion. And now he becomes negative. So he's looking. Does anyone have an electron for me? Anyone has an electron for me? Lithium goes, I do, I do. So if the two of them can get together, they are very likely for him to give his electron there. But now what happens is all of a sudden I have a particle that's positive and a particle that's negative, and they're attracted to each other. Okay, and so we get lithium fluoride as a bond. It's an extremely strong attractive force between them, a positive and a negative. They're not sharing that electron. Know this, that his lithium is giving away his electron. They're not bonded together because they want to share something. They're bonded together because there's a attractive force between them. Okay, so here we have lithium. So here we have our lithium and fluorine. Let's see, I'll draw fluorine larger. And the reason why I draw fluorine larger is because he is a larger molecule. Why is he a larger molecule? Because he has more yes, he's now filled up his second energy level, so he's got more orbits. The first one only has that one orbit. This one is bigger, so that's why I draw it like that. But then if I write in now, remember lithium is now positively charged. He's still positive, even though they're now attracted to each other. It's not all of a sudden neutral. It's like two magnets. Have you ever put two magnets, the positive and the negative, next to each other? Are they still magnetic? Does it still stick to anything? They don't lose their polarity, okay? So this is still positive and negative. They just now bonded together because of this perfect positive and a perfect negative charge. But as a result, we now get a molecule that works like a magnet. I have it's now called a polar molecule. Now, what a molecule is, a molecule is exactly more than one atom together, where all the atoms have they've got their fill, they have all their electrons, they don't need any more electrons. So a molecule is stable, okay? But this is a polar molecule. Now what happens in polar molecules is that I just want to give you a word that I haven't used, it, interatomic force. Interatomic force. An interatomic force is the force that keeps the two atoms together. Make sense? So they're attracted to one another because they're ions, it's attracted to one another, and it's an interatomic force that keeps them together. Now, when this happens, there's not just one lithium atom in the area, there's a bunch, and every lithium atom needs a fluorine atom in order to create lithium fluoride. Okay, so this is now called lithium fluoride. H in there. Okay, lithium fluoride. Okay, and when we give names, we always start with the cation and then the anion. Just like in the periodic table, your cation will always be the one on this side. And notice the ones here always has one electron to give, so he will always give one electron and become one positive. These ones will have two electrons to give, and so they will become two positives. These ones skip these ones, they call the transition metals, we'll get to them just now. Then these ones will have three to give, so they will have 3 plus. The 4 ones, well, they're starting to share, because I'm not really willing to give away my 4, because I can easily get, well, not easily get 4, but I can rather get 4 someone else or share with you, okay? But once it comes here to from here onwards, they start having too many electrons, so they want electrons. So they often either share with others that are willing to share, or they rather take electrons. So these ones become our anions because they get extra electrons. Make sense? So that's why when we name things, we will have something like sodium chloride, potassium oxide. You see, I name it from this side to that side, my cation and my anion. Make sense? Okay, see, still, we're using our periodic table for everything. Okay, I was busy telling you that now I have this lithium fluoride molecule, but there are not just one atom of lithium, there's more atoms. So there's another lithium fluoride hanging around. So I've got another lithium fluoride hanging around. Okay, here's my other one. Another lithium fluoride. It too has the same structure, of course. One side is negative and one side is positive. And it has interatomic forces keeping the two together. But now we notice that now I've got almost two magnets. And now what happens is these two magnets attract one another. The negative end of this one will be drawn to the positive end of that one, so that I end up get a structure like this. I get my structure like that. Here's one molecule, here's another molecule, another molecule, another molecule, another molecule, another molecule. So notice these molecules are attracted, and they're much closer. I actually did a terrible job here. They're completely stuck to one another. There's very strong forces in polar molecules. Okay, and this is called, this type of force, or this type of bond, this is called a bond when two molecules, when two atoms bond in such a way, because of the one being positive, the other one being negative, they're now attracted to one another. The interatomic forces, this is called an ionic bond, when it's two ions that get together. Ionic bond. Okay, and ionic bonds happen because one doesn't want his electrons, the other one wants to give it away. That's when it happens. Okay, and now in ionic bonds we'll always have polar molecules, and the forces that exist between polar molecules are very strong forces, which means the molecules, and that forces are called intermolecular forces. Intermolecular forces, that's the forces where particles attract one another. So it's intermolecular. That is a weird looking C and A. Okay, intermolecular forces is the forces that exist between the molecules. There's forces between the atoms, that's what make them bond. There's forces between molecules that make them stick together. Now, if I say that these forces are strong, what do you guys think lithium fluoride is? Do you think it's a solid, a liquid, or a gas? It would be a solid, because the particles are so attracted to one another that they stick together and they make a solid thing. So let me give you a very common one is sodium chloride. All of us know sodium chloride and consume it on a daily basis. This is, did you this morning?
Yep.
This is normal table salt. So let's see, why is this ionic? It's ionic because sodium has how many valence electrons? Chlorine has how many? 7. So chlorine can easily jump by just getting 1. Sodium is very willing to give away his 1. So he gives his 1 to chlorine. Chlorine becomes negative. Sodium becomes positive. Chlorine becomes an anion. Sodium becomes a cation. Do you guys get the picture of ionic bonds? It's very simple. Okay. And so that's called ionic bonds. Now let's look at another type of bond, and that is called covalent bonds. So the easiest way to look at it is to look at hydrogen itself. Hydrogen has only 1 little electron. Okay, so he badly just needs another electron, or he needs to give away his electron, but he only has 1. So for hydrogen to give away his electron is, I wouldn't say it's unlikely, but he would much rather just share. Okay.
He doesn't know.
So he's willing to share, and what he would give it away, and he does give it away often, and especially when there's other atoms that very badly want. So which are the ones, just based on the table, which are the ones that very badly want electrons? Fluorine, bromine, okay, they badly want. Now let me tell you also, fluorine wants electrons even more than chlorine. Let's quickly look why. Imagine I've got a 10 Rand note here. Akani, between you and Bill Gates, who would want that note more? It's obvious, but just tell me. You would want it more. But it's the same note. Like, why would you want it more than him?
Because he has more.
He has more. Relatively, it's more valuable to him than to Bill Gates. Okay, but let's reduce it. Bill Gates, it's obviously. How about between you and me? It's the same between you and me. Okay, so who do you think gets the most pocket money in this class? Or what is it not? Pocket money. What's the word?
Yeah.
Pocket money. Allowance. That's the word I'm looking for. Who gets fair allowance? Who gets none? You all get some. Okay. Well, let's say I was getting pocket money, Makani, you were getting pocket money, but you were getting more than I. Who would want the 10 Rand more? The one with the least. So, in other words, between fluorine and chlorine, both of them just need 1. Who would want it more?
Fluorine.
Why fluorine?
Because he's ace man.
He's got less electrons. He's only got 9 electrons. Chlorine has 17. Come on, chlorine, don't be so. I want it rather. Okay, so fluorine has a higher desire. Okay, oxygen only needs 2. Okay, he only needs 2. Oxygen has the second highest desire for electrons. He desires it even more than chlorine. Why? Because I only need 2 and I only have 8. Can you understand? After oxygen is chlorine. Okay. Now, how do I know that? It's called the electron negativity. Notice fluorine has an electron negativity of 4. Oxygen has 3.5. Chlorine is 3. So electron negativity is a measure. It's a number that tells me relatively how much does he desire electrons. And what you'll notice, and it makes sense now, that the desire for electrons increases as I go to the right. Because as I go to the right, I need fewer. So, for example, fluorine, I only need 1 more. So I've got a very high desire for electrons. Oxygen still has the option. I need 2 or I need to give away 6. So, okay, I have some motivation to give away because I don't have that many to give away. Fluorine has less motivation to give away because he has too much to give away, but he has too little. He has less than chlorine. Does that make sense? So, electronegativity increases to the right. In other words, my desire for electrons increases to the right, and it also increases to the top because as I go up, I have fewer. So 1 electron is worth more. So my desire for 1 electron is higher. Make sense? All of it makes sense. Okay, cool. So based on that, let's look at, and that's why I say hydrogen. You see hydrogen's is about 2.1. Fluorine is about 4. The smallest is about 0.7. Okay, so this is the lowest and the furthest to the right. This is the highest and the furthest to the top. Why do these not have any?
They fool.
They fool, they don't want. I don't want electrons. Screw it. Okay. So this is the highest, the top right, the highest to the top right. So can you see why these ones are so low? It's not that they don't want electrons. So it's not 0. Okay. But if they want, they need a lot. So I'd rather give it away. Like, does it make sense? So it's not 0, but it's not. So, but look here, between these, if lithium and hydrogen were to get together, who would get the electrons? Hydrogen. Hydrogen does have 1 electron, okay, and so he would give it away because his desire for electrons is 2. So for example, hydrogen and fluorine, who would get the electron? Fluorine, he's 4. He definitely gets that electron. Grab it out of the hand. Give me that. Okay. Hydrogen would then give it away. But hydrogen and lithium, who would get the electron? Hydrogen will get it because lithium says, well, here you go. Okay. So hydrogen can be hydrogen where he's given away an electron, making him positive. Or it can be hydrogen where he got an electron and is negative. An example would be sodium hydride. Sodium gave away his electron to hydrogen. Okay. Okay, so hydrogen can be either one of those two. Okay, so what type of bond would this be? Yes, interatomic is the forces inside, but what type of bond is it? It's ionic bond because sodium gave it to. This is a cation and that is an anion. Makes sense, isn't it? Okay, but now let's say hydrogen wants to exist by itself. So for example, let's say we have another hydrogen. Another hydrogen has the same structure like this. He's got 1 electron. Now the two of them come together, say, give me your electron, give me your electron, give me your electron. They've got the same desire for electrons. No one is going to give away his electron because their desire for that electron is the same. Make sense? So then they decide, okay, how about we share our electrons? So this one just comes a little closer, okay, and they now share their electron. So in other words, their two orbitals interact, and now they stick together because they've got a mutual interest. They're not drawn together because they're opposite poles. They're drawn together because I want this electron. It's almost like I've got a ball and you've got a ball, and I want two balls and you want two balls, so you hold my ball. I'm sorry, let's say stick. I'm sorry, let's say that. Let's use something else. A rope. Let's use a rope. I've got a rope. I want two ropes. So you hold the one end of the rope and I hold the other end of the rope. As a result, we stuck together because we're both holding on to the ropes. Okay. You guys think that's a strong bond?
No.
It's not. Well, no, it's a strong bond. It's not that it can be a strong bond as well. Again, depending on the electronegativity, how badly both of us want it. Because if I really want it very badly, I'll hold on to it stronger. But you also want it badly, so you'll hold on to it stronger. Okay. So that does add to the bond strength. Okay. So. What was I busy telling you? Okay, so this is not an ionic bond. It's not two ions. One isn't positively charged and one negatively charged. Okay? It is now called covalent bond. Co means together. What do you think valent refers to?
Sharing.
That's what the co means.
Valence.
Valence, it comes from valence. Covalence means we're sharing our valence electrons. Okay, does that make sense? But now look at the molecule. Let's draw these molecules the same way we've been drawing those other molecules. So here's my hydrogen molecule, and here's another hydrogen molecule. Okay, their orbitals now intersect, so that's why they together. Okay, their orbitals intersect. There's now in the whole molecule how many electrons?
2.
2 electrons. Okay, they travel around in the 2 orbits. They can be anywhere in either one of the 2 orbits at any time, okay, because they're sharing it, okay. So, is this molecule at any point, does it at any point have a positive or a negative charge? In other words, remember here, it was polar. At all times, one side is positive, the other side is negative. This one, does it happen that, well, it could happen, okay, if both of them are on the same side at the same time. Then all of a sudden this side becomes negative and that side becomes positive, okay? It could happen, but it happens so quick that all of a sudden it's normal again. And then maybe both is on the other side, so all of a sudden the negative is on this side. Do you understand? So because the space is so small, it's just this little piece of space. If they come together, it's just for, like, it's not even less than a second. It's just a brief positive. So in other words, if there is a charge, it is so brief that it doesn't even have an effect. The average of it, sometimes I'm positive, sometimes I'm negative, sometimes I'm neutral. The average is neutral. Make sense? Okay. So, do you think, is there a reason for it to attract other elements? Not elements, other, remember we said now, this is a molecule, and so there's another molecule. This one does not have a charge, not a charge, it's not polar, because it doesn't have poles, positive and negative poles. This one is not polar, Doesn't have poles. Okay, so will these two attract each other?
No.
No, not really. If there is any attractive forces, it's just momentarily. It's very slight. Okay, so this is now called hydrogen. We now call hydrogen H2. And because there's two hydrogens, it's called a diatomic. Diatomic, the di means two atoms. It's a diatomic molecule. And this one, do you think it would be a solid, a liquid,
Liquid.
or a gas?
It's gas.
This one would be a gas. Now why would it be a gas? A gas is particles that cannot stay together. There's no force, there's no intermolecular force. Well, there is, but it's so small that it's not enough to keep the molecules together. So if you have this gas in a container and you open the lid, there's nothing that keeps it together. It will start floating away, travel through space. Make sense?
Yes.
That's why it would be a gas. In order to get it to be a liquid, the reason why it moves, what type of energy is motion? Motion, if something moves, what type of energy does it have?
Kinetic.
Kinetic. So if I want to reduce its kinetic energy, I need its temperature. Okay, so if I want to keep the molecules together, I need to reduce the temperature. Because if I take away temperature, I'm taking away energy. Does that make sense? Where will I get the energy from? From their kinetic ability, the ability to move. So if I take away energy by taking away heat, they don't have energy to move, so they start sticking together and they become a liquid. Okay, then the more energy I take away, the more they get stuck together, until I've taken away all the energy that they have so that they can't move, and that will make them solid. Make sense? Good. Okay, this, as I said, this is called a covalent bond. So a covalent bond means I'm sharing my electrons. Let's look at another covalent bond. Oxygen. How am I going to draw it? Let's draw it like this. Oxygen. Let's go see. How many energy levels must I draw for oxygen? How many?
8.
How many energy levels?
Oh. Sorry.
In what energy level is he?
It's going to
Speak louder, please. Guys, what tells me the energy level? Rikus? The row. He's in which row?
The second row.
He's in the second. Does this thing have row numbers? No. He's in the second row. 1, 2. So 2 energy levels, which means I'm doing my s orbital, another s orbital, and p orbitals. Okay. Now I see I've got how many electrons do I have to distribute?
8.
8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. I need 2 more. Remember, I've got, and what type of orbitals are these? So I've got a p orbital here, and let's say this is the p orbital that came out of the page and into the page. Now these all have the same center, and then here's a p orbital that goes from left to right. Okay, so there's my 3 p orbitals. This one has both. This one only has 1. This one only has 1. So I need 2 more. There's 2 orbitals that need. Okay, if I go and look at his desire for electrons, he's got quite a high desire, 3.5, second highest on this periodic table. Okay, so along comes hydrogen. Okay, and hydrogen says, you know what, I'm willing to give you some of my electrons. Okay, but he also has an average desire for electrons. So what hydrogen does is he says, okay, we will share it. Okay, you can have my electrons, but we will share it. So hydrogen comes, and hydrogen shares his electron, and his electron is in an s orbital, because he just has this one. And so he's now connected here to this p orbital. Every now and again, this electron makes its way into his orbital, and now they're happy. Okay, he gets his electron every now and again. He shares his electron so that this one always has, but it's not enough. We need another one as well, because this one also needs one. So we need another hydrogen coming here, and he now shares his electron at that point. So again, there's now two orbitals. They've got, these two have their orbitals filled. Hydrogen has his s orbitals filled, and it's happy. So let me draw for you the molecule roughly. So let's say there's my oxygen molecule, and here's my hydrogen molecule, and my other hydrogen, sorry, not molecule, my oxygen atom, hydrogen atom, and my other hydrogen atom. Okay, now who will hog the electrons? Like here, did any one of these two have the ability to hog electrons?
No.
No, because it was that rope pulling competition. You have it and I want it in the same capacity. But this time I have hydrogen and oxygen doing a tug of war for those electrons. Where do you think, if this was a tug of war, who would be winning? Who would have more of the rope? Oxygen would be winning. So even though the electrons are being shared, they will spend more time closer to oxygen than they would on the hydrogen side, because oxygen has a strong desire for those electrons. That would mean that in this molecule, oxygen will have a negative charge. He will often have a negative charge. And since hydrogen is losing the tug of war, hydrogen will have, and it's not that oxygen has a positive charge, it's a partial positive. It's like it's almost positive, but it's not perfect as in ionic bonds. Does that make sense? But now we see, okay, now we also have other oxygen molecules. Okay, and that oxygen molecule will have a negative, an oxygen that's a negative, which will be attracted to that one's positive, and he will also have two, and these two will probably try and get away from that one, because like charges repel each other. So they will try and get away from that one. So this, again, this is now, I'm talking about interatomic or intermolecular forces. What am I talking about when I'm talking about molecules being attracted to one another?
It's molecular.
It's molecular forces. So this one is now attracted by that one. And now if I draw another one, where can I draw it? Okay, for example, I will draw one here. Maybe these two are attracting another one, another molecule there, and these two hydrogens are somewhere on that side being repelled by those. Okay, but can you see, do you understand what I'm trying to do? You see what I'm trying to do? I'm trying to show you that there's definitely attractive forces that exist. Do you think it's as strong as with ionic bonds? It's not as strong as ionic bonds, but it's still strong enough. So this time I'm not going to ask you, you know. Solid, liquid, or, man, am I going to keep spelling liquid? Liquid or gas? Which one? By the way, this is H2O if you didn't know what I was doing. So this is liquid. Can you see the forces aren't that strong that it will make a solid, but it is strong enough so that it doesn't evaporate. Okay, but again, if I add heat, I am giving the molecules energy, which means they have motion, which means they are able to escape, and that's how I can have steam is water with molecules that have enough energy to escape the attractive forces of the other molecules. Make sense, huh? Great. Again, if I take away water's energy, it becomes a gas. Now let me show you. So now we've had, this is called a polar covalent bond. Why do you think it's called polar? Olivia, why do you think it's called polar? What did polar mean? Take a guess then.
There's two hydrogens, maybe?
Mm-hmm. Pole refers to what? Polar. Pendile?
Polar means that there are two poles that are charged. So obviously, since oxygen is charged and glucose,
Hydrogen.
hydrogen is charged, then
Yeah.
there are different pinions trying to pull towards each other, even though they don't.
Exactly. So polar means that my molecule somewhere, like, okay, so a magnet has a north and a south, isn't it?
Yes.
Okay. In molecules, we have positives and negatives. Okay. A magnet can only have a north and a south. It doesn't have, it can't have two norths. Okay. But molecules itself can have two positives and one negative, or two negatives and a positive. Okay. Point just being is there's attractive forces. It's not as strong as in ionic bonds, because an ionic bond is literally a permanent pole. Okay. While these aren't necessarily permanent. Now, just something interesting now. If I take something like oil, why does oil not mix with water? Who knows?
Isn't it because, okay, I don't know what the equation for oil is, but I'm thinking that since water is positively charged.
It's not positively charged, it's polar. Is that what you're trying to say?
Is polar.
Yeah.
And oil is, let's say for example in this case,
Oil is non-polar, I can tell you that much. Non-polar meaning
they don't have any.
it doesn't have a pole. It's like hydrogen. Hydrogen is non-polar. Non-polar because we don't have a positive negative charge. If it is, it's so brief, it doesn't, on average it doesn't.
Yeah, so how can you attract something that doesn't have?
Exactly. So if you mix water and oil,
isn't it because of the densities of the two substances?
no, because
It's polarity or something.
sorry.
The flow for
No, the reason why they don't mix, because for example, salt and water mixes. Salt dissolves in water.
Oh.
Why? Because salt, we saw, was ionic. Water is, salt is ionic, which means it is polar. All ionic bonds are polar. Water is polar. It's covalent, but it's still polar, which makes it polar, so they have the same charges. Now what happens is if you have, let's say in between here we push in another molecule and I'm going to try and draw it. I doubt I'm going to get it right. Another molecule here in the middle that's not polar. What is going to happen to this molecule? It's going to be pushed out of the way so that the water molecules can get together. And that's what happens in oil. When you pour oil in the water, it's being pushed. The molecules itself is being pushed out of the way so that the water can come back together, because they're attracting, water molecules are attracting one another. On the weekend, sugar is C is carbon, H22O11. I think sugar is, that's the formula for sugar. And you'll notice that all of these elements are ones that they won't easily give away the electrons, so they don't becomes covalent. The whole thing is a polar molecule, and this one is polar because of the 12 carbons. Okay, remember the longest, we're getting to that in organic chemistry, but 12 carbons is a long chain, which makes it dipole forces. So even though it's covalent and electrons are shared all over the place, because it's a long molecule, there's a high probability of electrons coming together. Okay, and then all of a sudden there's a strong positive at that stage, or a strong negative, I mean. But anyway, so sugar is polar. So I was frying this weekend, and I'm putting butternut in tin foil, and I want to put sugar and butter and cinnamon in the tin foil, and then you put it in the coals. And I don't have enough butter, so I mix the butter with oil, and I put sugar in. And do you know that sugar doesn't dissolve? It stays granularly in that. It simply doesn't dissolve. It just stays together. Like, why? Because sugar molecules are polar. It attracts the other sugar molecules. Even if it does dissolve, it immediately attracts each other again, and it sticks together. So that's why it doesn't dissolve. Anything, do you think hydrogen gas will dissolve in water? Hydrogen gas can't. It's non-polar. So who knows what gas do they use in Coke?
In Coke.
In Coke. Coke has gas in it, doesn't it? Carbon dioxide, CO2. Let's look at CO2. Okay, it's carbon and oxygen. Oxygen's desire is 3.5. Carbon's desire is 2.5. Do they have a big difference between their desire for electrons? It's not that big, but it's big enough so that the electrons will congregate near oxygen. Does that make sense? And this one will have 1 carbon, 2 oxygens. So we will have 1 carbon, looks like this, 2 oxygens. Okay? So we would have 2 negative and a positive pole. You see, and then also it's a little bit different than hydrogen, but it's still polar. And that is why carbon dioxide dissolves in water. Make sense? And why you shake it, then the gas particles come to the top and it starts evaporating, because it can't go back in. It doesn't have, yeah, it's on the surface now. So does it make sense? You understand how these things come together? This is solubility. Again, okay, so how could I know whether something is an ionic bond, a covalent bond, or a, let me show you that. So ionic and covalent would be on a scale. This would be pure covalent, and this would be pure ionic. Okay, so you'll notice as I'm going from lithium onwards towards this direction, lithium, or let's say from down here up to there, francium, that's the one down here, he would gladly give away his electron. Okay, so if francium and fluorine get together, that's almost like the easiest trade ever. Okay, because he's got a very low desire for his electron, so he will. This is Bill Gates and McCartney. Okay, but as I come more towards this direction, I start wanting to hold on towards my electrons, which means I am more likely, as I'm going in this direction, I'm more likely to share. Does it make sense? The only difference is hydrogen. Do you see he doesn't really fit in here? So hydrogen, if I had to move him, I'd have to put him somewhere maybe here. Okay, so that he fits in with this understanding. But now, as soon as I get to so from hydrogen, make a little, so imagine hydrogen is up here, where, I don't know, he's difficult to fit in here, I suppose up here, yes, up here, and you make a little line like this. Do you see there? Okay, these elements on the left hand side of that line are likely to give away their electrons. The moment you are likely to give away an electron, you are in one of two types of bonds: ionic or metallic. We've not looked at metallic, I'll look at metallic still. Okay?
If you're likely to give away
You're likely to give away your electron. So for example, sodium and potassium, if they are in a compound, it's either in a metallic compound or in an ionic compound. It's not in a covalent compound. Okay, so just start with that. The rest, these rest, if these want electrons, the guys on this side want electrons, they are likely, because they already have many, they're unlikely to give away. So they are either ionic, they would either be ionic or covalent. Okay. Covalent means they would be sharing. So I need maybe 2, so maybe someone will share 2 with me. Okay, I've got 6, who wants to share with me? Okay, so they're likely to be covalent or ionic. So in other words, these can never be metallic. Make sense? These can never be covalent. Okay, now the way that you would decide between covalent and ionic is by looking at the difference between electronegativity. In other words, looking at the difference between electronegativity. So how badly does the bigger one want it and the smaller one want it? So you do a calculation. So if it is less than 1.7, so the biggest difference it can have is obviously between fluorine and francium, and the biggest difference there would be 3.3. Okay. What would be the smallest difference? I'll tell you just for time's sake. 0. That is when I want to share with myself. Not with my, like hydrogen and hydrogen. What's the difference between their electronegativity? 2, was it 2.2, 2.1? 2.1 minus 2.1 is 0. You understand? So the smallest would be. So if I'm sharing with myself, or if a compound like O2, H2, these are all covalent bonds. They're also non-polar. Why? Because we're sharing it equally. And it makes sense. Now half of this is about 1.7. So bigger than 1.7 would be ionic. But now, in other words, imagine it like this. Okay, we share, 2 of us, I'm sharing with someone. The stronger that guy pulls, at some point he can pull it out of my hand. Then it becomes if we're pulling, both of us are pulling on an electron. Both of us are pulling. If I'm stronger than you, we become polar, isn't it? Because I'm now getting the electron on my side. If it's strong enough that I can pull it away from you, what type of bond do we get? Ionic bond. Because now I'm an ion, I got an extra electron. Covalent would just mean I'm hogging it. I'm hogging it, that's why I'm polar. If we're pulling roughly the same, it is it's covalent because we're sharing. We're both pulling on it, but we're pulling roughly at about the same. So in other words, that would be non-polar. So at about here, I can't remember what the exact value is, but the values aren't necessarily that important. If it is more than 0.4, then it means that I am pulling it more towards me. So I'm starting to have a partial negative charge on the one that has the bigger pull. So for example, notice water. When oxygen and hydrogen pull, the difference is 3.5 and 2.1. So 3.15 minus 2.1 is 1.4, which makes it, so in other words, this is covalent, this is ionic. Everything higher than this is polar, and everything lower than this is non-polar. Again, it is not, when it comes to polarity, it's not you're in this box or in that box. You become more polar or less polar. The more polar you become, the stronger the forces between the molecules. And so the more likely you are to be a solid. Make sense? Okay, so which one is this? Non-polar or polar? Water. So we got the difference between electronegativity was 3,5 minus 2.14. Hydrogen gives me 1.4. What does water fall under? So water is a polar, covalent polar. Do you understand? Okay. Now this does not work. The scale does not work if I have two elements from this side, okay? Because two elements from that side is metallic. So why do I say that? That's because this is the alkali metals. This is the alkali earth metals. This is the transition metals. So let me explain to you why are metallic bonds excluded from this. So do you guys get ionic, covalent, polar, non-polar?
Yes.
Fairly simple, okay. But now metallic is slightly different. Here when I think of metallic bonds, I think of hippies. So here's iron, okay. Iron can have, because transition metals doesn't necessarily have the same number of valence electrons than and so one iron molecule might have different number of valence electrons than another iron electron. So you'll see often they write something like iron 2 oxide. Okay. Now, what type of bond is this? Let's look. So, is it two elements on this side? No, there's an oxygen there, so I can use my table. I see it's 3.5 minus iron's 1.8. That gives me 1.7. So it would be about, was it 3.5 and 1. Yeah, about 1.7. So it's becoming ionic, isn't it? Okay, I would lean towards ionic. It is ionic. The reason why it is ionic is because if we look here, this 2 literally means how many oxygens did iron give? Not oxygens, electrons. Iron gave 2 electrons. That's what he did. So this is iron giving 2 electrons, and therefore he becomes 2 positive, and oxygen getting the 2 electrons, and that's why he becomes 2 negative. Make sense?
Yes.
Okay, and so we have 1 iron bonding with 1 oxygen. But so we have ions, and iron can sometimes be iron 3, so sometimes he has 3 electrons. See why I'm saying these are hippies? They're so inconsistent. Okay, so sometimes it has 1, sometimes it has 2, sometimes it has 3, but now he doesn't really want them. Okay, I'll share them. Who wants it? So other iron molecules have the same. They have electrons. They don't really want to give it away. They don't really want them. So another iron says, well, I'll take it. Give 1 to me. So he gives him one to him, and then he realizes, oh, now I've got too many, so I'll give 1 away. Okay. So another iron accepts the one that he's giving away, but he also has 3. So can you see how the electrons flow between other metallic atoms? They're giving it away, handing it over, because when I get 1 I become positive, so now I reject 1, and so there's the whole time in metallic bonds there's this sharing of electrons. So they call it a sea of electrons. Electrons are constantly flowing. Okay, no one wants to hog electrons, they easily give it away, and that is why metals are conductors. A conductor is something that allows electrons to flow through it, and that's exactly what metals do. They allow electrons to flow. So once there is a pool of electrons on the one side, then, oh, you need electrons because you've just given away electron. Here's an electron, here's an electron, here's an electron. You see, and there's this pool of electrons on the one side, and there's a stream coming from this side giving electrons. While do you think you're going to, do you think fluorine is going to give up his electrons? Okay, so if fluorine is part of a compound, you're not getting my electron. Move it. Okay. So, and this is metallic bonds. So we do very little about with metallic bonds, but that's also why metal, it remains a solid, because the whole time I have a positive charge because I'm giving away electrons, and you have a negative charge because you are getting electrons. So the whole time there's this connection between us, and there's a strong, so it forms solids. Very strong solids, but not as strong as ionic bonds. Ionic bonds are really very strong. I mean, if you, it's very difficult to break. But now what happens, for example, is if you take metal and you start trying to break it, doesn't it bend? Can you imagine if you had a solid piece of salt? It would be a crystal. Do you think you can bend a crystal? Imagine salt. When you try and squish salt, it cracks, it breaks completely. Okay, that's because of the type of bonds that exist in metal. It's this pliable. Okay, we're still sharing electrons. It's not. I don't know how else to see it. I can really see the fluidness of the solid. Does that make sense? Okay, so there's another property that comes from the fact that we're just hanging around our electrons. What I want you to notice, guys, is that you notice how everything is about these electrons. It's all about how we share and give away electrons. The strength of acid is about how badly, remember, acid is defined as something that donates protons. Can you donate not donate a proton, but donate hydrogen? Okay, when will I donate a hydrogen? If I can steal his electron. Does that make sense? Because hydrogen H+, H+ is acid is something that is able to donate hydrogens. Now, when will I donate a hydrogen? If I've stolen his electron. He becomes a hydrogen without an electron. You know, why is hydrochloric acid such a strong acid? Because chlorine has such a strong ability to steal hydrogen's acid. It's hydrogen's acid, hydrogen's electron, I mean. So if we go back here, chlorine has such a strong, you see 3.5, he's got that high ability. Now, something else that you also need to consider, it's not just that, it also has the ability, it's also about how easy it is to break the original bond. So, for example, hydrofluoric acid, okay, is not as strong. It's actually a weak acid, even though he's got a very high desire for that electron. To break the bond between hydrogen and fluorine is difficult, okay, and that's got to do with the size of the molecule. So the bigger the size of the molecule, the easier it is to break the bond. So chlorine, this, you can look at the mass roughly as the size of the electron. So chlorine has almost double the size, and it's got a high electron negativity, and that's why it can easily break the bond with and steal the electron and then give the hydrogen H+. That's just as an example. Okay. What else did I want to tell you? No, I think when it comes to the basics, this is as much as I want, as far as I wanted to go. Do you guys have any questions for me based on this? I'll go over now. We'll just take a short break. You need to go soon, and we'll take a short break. So let's say till 11, and then we'll go on to moles and mass. There's just a few things I want to say there, and we'll look at an exam type question where we use a lot of what we spoke about now. Okay. This, however, isn't examinable. It's not something they're going to ask you in an exam. Okay, so in your chemistry exam, let me say that might be helpful. In your chemistry exam, you're going to have, I think it's 9 questions, but it doesn't matter. Question 1 will be your multiple choice. Question 2 will be organic chemistry. It will be a random, like, name, give isotopes, it would be a random bunch of things. What is the molecular series of, homogeneous series of whatever. Things like that. Then question 3 will still be organic chemistry, and it will either be organic chemistry reactions or organic chemistry properties, and you'll see how this understanding of the forces between molecules based on their polarity will really help you understand the property of molecules. That's maybe something I haven't mentioned. Let me just quickly go and mention that. There's one thing that is slightly confusing, and that is something called a hydrogen bond. So we've looked at covalent bonds, ionic bonds, and metallic bonds. Hydrogen bonds is not a type of bond. It's actually the wrong word. It shouldn't really be good, because remember, bonds are about interatomic forces. An ionic bond is about how the two ions bonded, and those are two atoms that bond. Covalent bonds are how two atoms shared electrons, and that's why they stay together. Okay. Hydrogen bond is not hydrogen, that is not how hydrogen has bonded to something else. Hydrogen bond is actually an intermolecular force. I'm just going to say IMF. You know what I mean, eh? Mm-hmm. In other words, it's a force that exists because hydrogen has bonded to, okay, so hydrogen bond is a force that exists because hydrogen has bonded to a molecule or a high electron negative substance. Okay, so what do we mean by that? Water, for example, remember we said water was a covalent bond that was polar, and it is a covalent bond polar because the forces that exist between the water molecules are hydrogen bonds. So again, almost think of hydrogen forces, hydrogen bond forces. Okay, so what is hydrogen bond forces? Let's just put forces there at the back so that you don't get confused with the word bonds. It's hydrogen bond forces. What would be a hydrogen bond? It would be a hydrogen connected to a high electronegative element. So what elements could that be? That could be fluorine, chlorine, oxygen. So when hydrogen bonds to these oxygen, fluorine, chlorine, bromine, iodine, sulfur, okay, what happens is because they are electronegative, they're pulling hard on the electrons, and as a result the molecule becomes polar. And because the molecule becomes polar, the forces that exist between the molecules are quite strong, and then we get liquids. Now, one application why I said it's now important to mention here is when we get to organic chemistry and we get to properties, what forces exist in alcohols? Remember, an alcohol has an OH in it. That is a hydrogen bonded to a high electronegative. So alcohol has hydrogen bond forces. You get that? Aldehydes as well. I think it was aldehydes, I can't remember the other one. Has hydrogen bond forces. Hydrogen bonded to, no, is it carboxylic acid? Yeah, I think it's carboxylic acid. But carboxylic acid might just be offset by the oxygen. I can't remember what the other one was. We'll get there next week and we'll put it to memory. Okay, but just as a foundation now for this week, when we get to organic chemistry next week, we'll mention this. So, so hydrogen bond forces would be exactly that. And so, for example, alcohol, even though we have something like ethanol, ethanol only has 2 carbons, but because of this hydrogen bond, because here we have a negative charge on the oxygen and a positive charge there, another ethanol molecule will have a negative charge and a positive charge there, and so they will be attracted to one another. So ethane is a gas, 2 carbons connected to hydrogens. But ethanol, alcohol, is a liquid. Okay, a very vaporous liquid in the sense if I leave it open it will evaporate, so the forces aren't that strong, okay, but it's strong enough to make it a liquid. Do you understand? Do you understand how these become important when we now start looking at the properties of elements? Why the type of forces that exist tells me in what form we will encounter it at room temperature and what the boiling point and things like that would be. So I won't say too much more on that. I was busy telling you that would be question 3 and 4 would be organic chemistry reactions and organic chemistry properties. Question 5 will probably be something like reaction rates. Question 6 will probably be a question about equilibrium. Question 7 will probably be a question about acid and bases. Question 8, electrochemistry. Question 9, probably, or not probably, it's the last question about would be the fertilizer industry. I hate that topic. I hate it. Hopefully it gets better this year. Okay, anyway, so in terms of that, notice what we talked about today, there's not a question about it. Understand? So if I say it's not examinable, I don't mean it won't be in the exam. I mean there's not a question in the exam about these things. But in the questions, these play a role. Do you understand what I mean? So they might now ask you to explain why something is evaporating. And then you explain using the concept of the forces that exist between particles. What type of forces is it? Was it an ionic bond or covalent bond? They might ask you why is hydrogen a gas at room temperature? You understand? Questions like that. So it can be in the exam, but it's not a question in the exam. Make sense?
Yes, sir.
Cool. Okay, so let's stop it.